Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand humans? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello, welcome to this week's edition of Ask the Naked Scientists with Chris Smith and with me, Matt Jamison. You've got a bit of news there, first of all, haven't you?
Yes, I've just been watching the press release that NASA have put out tonight, which is all about Mars, because The Sun ran a story on this today. In fact, they released this a little bit before everyone else knew about it, but NASA have been watching Mars for some time from space using Mars Express. And this is a satellite in orbit around Mars, and one of the things that NASA Express is equipped with is a spectroscope. And a spectroscope is a way of analysing things by looking at the spectrum, because all chemicals have their own unique colour fingerprint. They absorb or emit light at certain characteristic frequencies which we can see, and that means we can single out what those chemicals are. And by using the spectroscope on board these satellites around Mars, what NASA have spotted is methane. Now, that doesn't sound amazing because you think, well, methane, it's just natural gas, it's the stuff we burn. But methane has to come from somewhere. Methane is a molecule of hydrogen, 4 hydrogen atoms stuck to a carbon atom. And this is a complex chemical, and it's produced, we think, by life. It must have a biological origin, potentially. So NASA are saying this might be a hallmark of life on Mars. So David Bowie could have the answer to his question quite soon. But it may also have geological origins. But what's really exciting about this is that they've spotted some vents on the surface of the planet where this methane comes out. And it comes out in summer and springtime, but it doesn't come out in wintertime. Now, why this is interesting is when the summer warms the planet, you would expect the temperature to go up and therefore the life to flourish and therefore to produce more methane. And in wintertime, when it's colder, the life goes to sleep and you produce less methane. And because it's coming out in these discrete places through these vents they've spotted, that means that will be a very good place to focus the future searches for life on Mars, so they can home in on those particular areas and see if there are bacteria there. Methanogens is the kind of bacteria, or simple forms of life that could be metabolizing things like carbon sources and mixing them with hydrogen atoms to make methane. And we think that the same things probably were thriving on the early Earth back about 3 billion to 3.5 billion years ago. And we think that actually the fact that we're here, we owe our existence to similar organisms on Earth, because by putting methane into the atmosphere of the early Earth, they warmed us up, because the sun was a lot weaker 3.5 billion years ago. And by having methane as a greenhouse gas in our atmosphere, it warmed up the planet, made everything warmer, and this helped more complicated life forms to get going.
What actually happens if and when we discover there is life on Mars? Do we send someone up there, or how does it work from there?
Well, there is actually a whole field, and it's called astrobiology. The concept of looking for life in space is this field of astrobiology. And they've drawn up protocols about how you deal with this kind of thing, because it's an important question. You want to be very sure that you don't contaminate the life, because anything we put into the system could potentially damage that system, and you also could be facing a threat from that material itself. It could be dangerous to us. So therefore we have to be very careful about how we keep a distance, a safe distance between us and them and us. And so that's why spacecraft are kept sterile, if possible, or as sterile as possible. And also that's why we don't have any plans to bring back bits directly from the surface unless we can do it in such a way that we can have some kind of containment around them. But the answer is that if there is life there, it will obviously be very intriguing and very exciting. But what we'll want to know is what's the nature of that life, because getting some analytical equipment to the place where you find that life and then being able to analyse it chemically and biochemically is going to be really critical, because you want to know, how does it metabolise? Is it like us? Does it have genetic material like we do? And if it does, that's going to be an amazing thing, because if it does, that sets the question, well, where did it come from and how did it get there? And where did we come from, for that matter? Because is there a common source? Is panspermia, the theory, true then? There's this idea that life was spawned somewhere in the universe, and it's ferried around space by various bits of intersolar materials which then land on hospitable planets and seed life there. That's one theory of where life came from. So if we do find life on Mars, and it's very similar to what we've got here on Earth, people will be asking a lot of questions.
How come we can land on the moon, yet we can't land humans on Mars?
Well, I think that you have to think of it in terms of the order of scale here.
Right.
The Moon is our next nearest neighbour, and it's a blink of an eye away from the Earth compared with the distance to Mars. Mars is millions and millions and millions of miles further away from the Sun than we are, and it's millions and millions and millions of miles away from us. And so to get there is a very long journey. And we just aren't good enough at space travel yet in order to keep people safe, sustain people for that long, get them to Mars, and when they get there, of course, they've got no facilities. There's nothing for them to eat, there's nothing for them to drink, so we have to overcome that problem for a start. And then it's the whole question of getting people onto the planet, getting people off the planet. How do you do that? It's not easy at all.
OK, the first question this evening for you, Dr. Cross, goes a bit like this. How does solar heating, how is it controlled?
OK, well, it depends what sort of solar heating you've got, but I'll talk generically because I've actually used solar heating because when I was little, my mum had a swimming pool and it was entirely solar heated and it never actually cost anything to heat in many, many years. In fact, that solar system is still working and it's surprisingly simple. And the way it works is that you have a bank or an array of solar panels which are made of very dense, thick polypropylene plastic, makes them very tough. And you pipe water from your swimming pool, or in the case of a domestic system, from your hot water tank, and it's pushed in at the bottom of the solar panels and flows upwards towards the top. And you do that so that the water forms a thin, continuous and homogeneous film up inside the panel. The panel collects heat from the sun because it's a black surface. It doesn't reflect any of the sun's light back off the surface. That's why it looks black, because it's absorbing all of the energy that hits it. That energy is then transferred as heat into the water, the thin film of water inside the panels, which flows to the top of the panel and then is collected into a collecting tube and returned to your domestic hot water tank or your swimming pool. Now, you have to decide, well, when do I put the water through those panels? Because if the water inside the panel is warmer already than the energy that it would gain from the sun, then it's going to net lose heat. So you only want to put the water through the panels when they're actually going to gain some heat. So how do you control for that? Well, there's a system built into these kind of arrangements which has a motorised valve, and the water is circulated bypassing the solar panels until a sensor made of exactly the same material as the solar panels on the outside and facing the sun, and which is comparing the temperature of the water and the temperature of the sensor, says, if you put water through here, you will gain some heat. And at that point, the motorised valve can open and it bypasses the normal route and sends the water through the panels and then brings the water back in and then back to the pool or the tank. And that system works incredibly well because it's dynamic. You can turn your panels on and turn them off to get water through them only when it's actually going to gain heat. And that way they don't act as giant radiators and warm up your roof. They only are absorbing energy, putting it into the water and heating the water up. And you can get really quite hot water out of panels, especially the high-efficiency ones which have glass in front of them to insulate them, and where the plumbing is insulated, you can get the water to be really rather hot.
Now, we're just going back to the space story we were talking about before. A comment coming from Malcolm in Lowestoft. I'd be interested in what you have to think about this. I just think the whole thing is a waste of money, space exploration. The object is to find a habitable planet, which obviously is not in our galaxy solar system. We should be spending the money on Earth-based projects, not giving it to NASA to waste. What's your take on that?
Obviously, it's very important to solve key issues here on Earth too. But the one thing to bear in mind is that often when you're trying to solve difficult problems, there are spin-offs. And those spin-offs have an earthly benefit too. So let me give you a little example. When I was going to Australia about 4 or 5 years ago, I stopped off in Singapore and I ended up in a stem cell bank. That may surprise some people that there is such a thing, but this is a system where people, when they have a baby, the umbilical cord blood, which is the connection between the baby and its mother, that blood is very rich in stem cells. And there's a practice in some countries of collecting that blood, extracting the stem cells, and then storing them on liquid nitrogen until the baby, when it turns into an adult, might need stem cells in the future, because they're very good stem cells and they're also genetically perfect for you. So there's this industry that's sprung up around storing them. The problem with these collections of these stem cells is that there aren't very many of the stem cells. In fact, there are very few and often not enough to treat a big, chunky adult. So how do you make more? We need to find a way of growing the cells. And the people, when I was in Singapore, produced this stuff, and it looked like If you imagine the foam from a seat cushion, which had been turned into a black metallic substance, so it looked like foam, but it was hard and black and metallic. They showed me this substance, and they said, "What do you think that is?" And I said, "I've not the faintest idea." And they said, "Well, this was originally the catalytic converter for a rocket engine from NASA." And NASA decided in the end to go with a different technology, but someone in the course of developing this put it under an electron microscope. And here is a picture under the electron microscope of this material, and here is a picture of some bone marrow. Can you tell the difference? And I honestly almost couldn't. They were almost indistinguishable under the electron microscope. And they said, and when we did experiments with this, we found that if we added the stem cells to this matrix material that was going to be a rocket engine, the stem cells grew really well. And we didn't have to add any growth factors. We didn't have to stimulate them in any way. We didn't have to add any other chemicals. The cells just grew because they thought they were in the body because it was so like the body. And this has enabled them to massively increase the number of stem cells that they can produce in dishes and therefore turn what would have been too few stem cells into the right number of stem cells for a person. So there's a direct example that I personally have had or come into contact with of how something developed with space in mind has had a direct earthly spin-off. And no one would have gone in that direction and had that benefit had it not been for the aim of trying to understand space better. And at the same time, let's look at what most of us got in our pockets. We've got mobile phones. We've got GPS devices. Our cars tell us how to get from A to B. We couldn't do that without satellites. But unless somebody had been forward-thinking enough, and in this case it was initially the Russians racing the Americans to get satellites into orbit, if they hadn't been doing that, we wouldn't have that technology. But it was getting things into space which has enabled those technologies, and they're changing the world. It means that when someone has an accident, we can pinpoint where they are and go and rescue them very quickly. People don't get lost so easily these days. Communications have never been better. And that's all down to the space race. So I think you have to think outside the box. And yes, it is expensive, but in the grand scheme of things, it's not expensive, given the other spin-offs and the fact that we're only on this planet once, and we need to answer these questions.
Very, very good answer. Can I just pick you up on one part of that, with the stem cells in the umbilical cord? If you can get a few of those, although there's a small number of them, is it possible to duplicate the DNA of those to make more stem cells for the bigger body later?
Well, that's what they want to do. The problem is that when you try to make the cells grow, they'll only grow if you give them a signal that tells them to grow. And the only place you can get that signal is from plasma. And not many people are going to give up their plasma because it's got growth factors in it. You have to use animal serum. And if you use animal serum, that may contain infectious risks. We're worried about things like BSE. Well, that could be a risk. So you don't really want to add growth factors and serum if you can avoid it. Also, people who don't happen to like eating animals, they're vegetarians or they object on religious grounds, that's a problem for them. And at the same time, when you add these growth factors, the cells do what's called differentiation. They become more specialised, and this is because we haven't got the cocktail of growth factors quite right. But by putting the cells in their own natural environment, or at least fooling them into thinking they're in their own natural environment, like a bone marrow, for example, that's how you can grow these blood stem cells to very high numbers without them specialising or differentiating. And that's really the value of that technology.
The question we're going to ask now goes a bit like this. What is a headache? What causes it? And what is actually happening in the body or brain, Dr. Chris?
As someone who gets headaches from time to time, don't we all? You often think to yourself, well, why the hell has this happened? The answer is that there's a number of causes for headaches, as you might expect. The most common kind of headache is a tension headache. Now, the muscles that control your scalp and your forehead run right the way across the back of your head. So they go from the front to the back, and you also have muscles that run up your neck and into the back of your head. And when you get very stressed or tensed, you're tense and you hunch up. You might hunch over your desk, for example. You might pull a frown continuously, for example, because you're stressed. Those muscles are applying enormous amounts of tension across the top of your head. And with that happening chronically over a period of time, it gets very uncomfortable. So that's called a tension headache. And it's usually linked to a period of intense stress or prolonged stress or repeated stress. And that's probably the most common kind of headache. Other kinds of headaches come from trauma. if you hit your head, obviously, and you get damage to the surface of the head, the skull and the bone, that is very, very painful, but it tends to be quite focal. Another common kind of headache is, of course, a migraine. And migraines are a bit more specialised because they're a brain blood supply phenomenon, so they're a kind of neurovascular event. And we know a bit about migraines, but obviously it's impossible to zoom in and see exactly what's going on inside people's brains when they're having one. But what scientists think is going on is that you get initially vasoconstriction, so you get clamping down of blood vessels inside the brain, supplying one side of the brain, and specifically the visual areas of the brain. And this is when people get what's called the aura prodrome. So when someone's first about to get a migraine, they start to describe a wiggly line and colours which seem to occur across the centre part of the vision on that side. So when you look at, if you're having this on the left side of your visual world, for example, that means the right side of your brain is experiencing the migraine. And that gives way to a throbbing, very, very painful headache that's often associated with photophobia. You can't stand being in the light, and you also feel sick. People often say they feel nauseated, and they may even vomit. And this can last for a number of hours. It can be so painful that people actually find themselves wanting to curl up and die. They say it's incredibly, excruciatingly painful, and they can't bear sound and they can't bear light. And then it slowly resolves and goes away. And when that happens, it seems as though what people think has happened is that the blood vessels have opened up and got bigger than they should do. Scientists don't know why these blood vessels do this, but they think there might be abnormal electrical activity in certain parts of the brain that are precursory to this occurring. And there was a study which was done a couple of years ago where a scientist decided to try something called transcranial magnetic stimulation. This is where you take a very powerful magnet and hold it near the brain, and because the brain is an electrical organ and magnetism and electricity are bound up one and one together, you can use magnetism to affect the likelihood of getting, you can actually use the magnet to control the brain. And for instance, if you hold it over the brain's motor area, you can make, say, the person's arm move totally involuntarily. And he found that when people came to the casualty department, this guy in America, if he held his magnetic stimulator over the back of their head, and he didn't tell them if he turned it on or not, he gave them either a sham treatment, didn't tell them it was off, just held it there, and in other people he gave them real treatment. The people who got the real treatment got better much quicker, and all reported relief much sooner than the people who had the sham treatment, suggesting that it really did work. So we think it's overactivity of certain bits of the brain that are triggering the migraine. There are also other headache phenomena. There's one example is cluster headache, and this is often young people, and you get these clusters of headaches that come all together, and they tend to be excruciatingly painful, but then they can go away again as soon as they came. And often you see this in young men too, but we don't know what causes that. And then there are the kinds of headaches that are associated with bleeding. Now, the brain itself, although it's got billions of nerves in it, has got no sensation. You could actually reach in and chop a hole in or scoop out a lump of someone's brain, and they wouldn't actually be able to feel you doing it. But the surrounding layers, the meninges, the layers around the brain, are very, very sensitive. And if you bleed into the meningeal space, so into the fluid around the brain, or between the layers of surrounding the brain and the bone, that's called an epidural hemorrhage. This is excruciatingly painful, and people do report sudden onset of very, very dramatic pain, and this is also known as a stroke, and that can be very serious. And of course, the other reason people get very bad headaches is if they have meningitis. You have inflammation of those meninges, and this can be caused by two things: viruses or bacteria. Viruses cause what's called aseptic meningitis. This is a viral meningitis, and it's much less dangerous, and people tend to recover uneventfully, and it makes you feel unwell for a while, but you get better. Bacterial meningitis is life-threatening, and this is when you have bacteria which get into the fluid surrounding the brain and into the meninges, and they grow and they inflame those tissues. And the most common used to be Neisseria meningitidis, until in young people in their early 20s it was called strain C, Neisseria meningitidis, but these people are all now vaccinated, and we've seen a dramatic reduction in the numbers of cases of that, thankfully, because it was very often it could be fatal. It's a very serious disease, and you need to pick it up quickly and treat people promptly in order to stop them having a problem. But most of these headaches, if they're simple headaches, they respond to several things. One is making sure you've drunk plenty. Drink plenty of water so you're not dehydrated. Avoid caffeine because it seems to make it worse. It especially exacerbates tension, and this makes tension headaches much worse. Take some simple pain relief like paracetamol, very effective, and then remove yourself from the stress. So do something quiet for a while, settle down, and hopefully it will go away. But if it's one of the other causes, the cardinal things to look out for, especially with meningitis, are a rash and other non-specific symptoms of feeling very unwell for a period of time, then the photophobia, being scared of the light. If you have those kind of things happening, that's a reason to go and get checked out.
Fascinating answers to fascinating questions. We're going from headaches to wind speed now. A question from Mike in Colchester. He understands how you would measure wind speed on the ground, but he's interested in how you would measure it in the air. For example, measuring headwind and tailwind on an aircraft at, say, 40,000 feet doing 500 miles an hour.
Well, the plane knows how fast it's travelling, and it can measure, therefore, the speed of the wind that's going past it. So planes do exactly that. They know exactly how fast the wind is passing them. So they can do simple subtractions to work out how fast they're going, because a good analogy to this is a boat. If I get a boat on the surface of the sea and I turn my engine on and I'm doing 10 knots, let's say, in one direction, well, I'm doing relative to the water 10 knots. But if the water is also moving, then I have to add the speed of the water to the speed of my boat. So, for example, if I measure relative to the seabed the speed of my boat, if the water is moving in the same direction as me, also at 10 knots, then relative to the water I'm doing 10 knots, but relative to the seabed I'm doing 20 knots. If the tide is going the other way, for example, at 10 knots, and my boat's doing 10 knots, I will be moving relative to the water 20 knots, because the water's going one way, I'm going the other, so my speed over the water is 20 knots. Over the seabed, I'm not moving at all. So the way the planes are doing it is that they know their position in the air, and relative to the ground, they can work out what their speed is. But they can also measure the wind speed, and by working the two relative to each other, you can work out what your real speed over the ground is and what your air speed is, and they can be two totally different things.
I was wondering what Chris' thoughts were on a theory Danish scientists have come up with, that cosmic rays are affecting the temperature by forming clouds.
Yeah, this has been a theory for some time, and scientists in Germany at one of the Max Planck Institutes first provided evidence for this in about 2002, I think it was. And what they did was to show how cosmic ray particles are linked to cloud formation. Now, what are cosmic rays anyway? What is the cosmic angle to this? Well, the Sun is this massive nuclear reactor which sits at the centre of our solar system. It's a million times the size of the Earth, so it's absolutely huge. And from the surface of the Sun is this million-mile-an-hour maelstrom of charged particles, which is literally running a million miles an hour. It's like a wind. It's called the solar wind. And it surges across space as this shower of charged particles, and it slams into anything in its way. Now, the Earth has a magnetic field, thankfully, and this magnetic field is what protects us. If we didn't have a magnetic field, then that solar wind would go surging past our atmosphere and pluck away the outer reaches of our atmosphere, slowly diminishing our atmosphere until we ended up like Mars, because Mars, about 4 billion years ago, lost its magnetic field because it cooled down and it lost the ability to make magnetism, and it got desiccated. We luckily have still got a magnetic field, so we didn't. But that million-mile-an-hour maelstrom deploys into the outer reaches of our atmosphere charged particles. And these charged particles are responsible for all kinds of natural phenomena, including the aurora borealis and the aurora australis, the northern and southern lights, respectively, because that's where these particles slam into other aspects of the atmosphere, oxygen, for example, nitrogen, and excite those atoms, and when they get excited, they glow, and that's why you get the northern lights. But at the same time, these charged particles could be linked to the formation of clouds. How? Because little clusters of charged particles attract other particles to them. So if you have them in the atmosphere, then they pull in bits of dust, they pull in even dandruff, plant matter. We know there's dandruff from animals and people in clouds because scientists have measured it. And when you have these little specks of dirt in the middle of clouds, that can act as a seed for the formation of water droplets, because when water is in the atmosphere in the formation of free water vapour, you have water molecules drifting around, and they find it very hard to start to get together to form a droplet because it's not energetically very favourable. When you have molecules spread out, you have to go against the laws of physics, entropy, to draw them together into a droplet. So there has to be some kind of payback or something to help the process. And this is in the form of nucleation. You have these tiny particles which help water to form into droplets. It gives them a surface to form on. So these charged particles, attracting bits of dust and dandruff and bacteria even, can act as these surfaces to enable the water droplets to begin to form, and therefore they could be responsible for helping clouds to get started under certain circumstances in the first place.
We're going to go to Terry in Ipswich now. If all the compressed air was let out from all the compressed canisters in the world, would that affect the atmospheric pressure on the Earth, or would it balance it out?
It would make absolutely no difference whatsoever. It would make a difference if you had a machine accurate enough to detect it, I think. But the bottom line is that relative to the amount of atmosphere we've got, this would be a tiny amount of gas and would therefore make an imperceptible difference. The atmosphere is so big that every square metre of the Earth's surface at sea level feels a force of 10 tonnes. So every square metre of the surface of your body has a weight of air equivalent to a London bus standing on it. And that's just the weight of the atmosphere pushing down on you. And you can see the effect of that when you go up Everest, because you can't breathe very well at the top of Everest. There's just as much oxygen in terms of percentage. There's 21% oxygen in the air that you breathe. But because there isn't that weight of air pushing down, the air is much less dense, it's much thinner. Therefore, in real terms, there are far fewer molecules of oxygen, so you find it harder to breathe. And so the atmosphere is absolutely massive, and the amount of air and gas stored in compressed cylinders is a fraction of that, and therefore you would not notice any difference, apart from a lot of noise as they all hissed and unleashed their contents, of course.
Dr. Chris, Paul in Clacton says, explain what goes on in your body when you get sciatica.
Yes, well, sciatica is related to the sciatic nerve, which is a very big, juicy nerve which runs out of your lumbar spine, down the back of your legs. It goes across your buttocks and then down the back of your legs towards your feet. And it supplies sensation and some muscle fibres as well to the skin and other tissues in your legs right the way down the back. Now, because it supplies those areas, normally when there's stimulation to an area supplied by the sciatic nerve, you feel the stimulation in that area. But if you accidentally squeeze the nerve somewhere along its course, then it thinks that the squeezing must have come from the area of skin or the bit of the leg that it supplies, and so you feel the pain in that area. That's called referred pain. And what can happen with sciatica is that where the nerve comes out from the spinal cord at several sections or segments of your lumbar spine, the nerve can get pinched off or squeezed. This is often caused by a slipped disc, for example. You have between the bones in your spine these lumbar discs. These are a thick fibrocartilage disc which is filled with a jelly-like substance. And the idea of these discs is to act like shock absorbers, so when you jump and land on your feet or you bend and stretch, they can take up some of the slack between the bones, acting as padding and shock absorbers. But sometimes the thick fibrocartilage ring round the outside that holds them in shape can weaken, and this allows the jelly-like substance in the middle to bulge through the back of the disc, or through the front of the disc, accordingly, wherever that weakness is. And this can lead to it impinging or squeezing the nerve coming out of the spinal cord and going out down the back of your leg. So because the nerve gets squashed, the nerve thinks that it's being stimulated or irritated from the patch of skin that it's supplying. So you feel the weird sensations of sciatica, which is usually a shooting pain down the back of your leg when you bend. And it's nothing wrong with your leg at all. The pain's actually coming from your back. When this happens, the best way to treat it is by rest, but not too much rest. You need to keep moving because otherwise you could get stiff and make things worse. But definitely with some anti-inflammatory drugs, and things like ibuprofen are brilliant, and you can also mix that with paracetamol. And this helps to damp down the inflammation, and it might make things a bit better. And if you get any kind of weakness, muscle weakness or anything like that, so in other words you get focal neurology, you must see a doctor. But you should give it a little while. If it doesn't settle down, you should see someone anyway, because this condition can sometimes or does sometimes need surgery to correct it, to deal with the slipped disc. But usually it settles down with simple pain remedies, and then you're okay as long as you don't overdo it.
That's it for this week. Thanks for listening. Remember, you can send The Naked Scientists your questions by email. chris@thenakedscientists.com is the address to write to. And if you want to find out more about The Naked Scientists, then drop by our website, nakedscientists.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.